So, but mathematics can be used for making our world not only nicer, but also safer, and also to save environment in some sense. So you are now here in the Baltic Sea. I mean, I think that many of you are from the Baltic Sea Basin, and many of you know that 80% of international cargo goes over sea transport. But I think that nobody knows that from this amount, 15% of world international shipping cargo goes over the Baltic Sea. The Baltic Sea is a tiny parcel of water, I would say, 400,000 square kilometers, more or less like New Zealand. If you push strongly on the Baltic Sea, New Zealand pops out from the other side. And 15% of world cargo goes over here. So 200 tankers are every day sailing the Baltic Sea. So if there is so high our scale accidents, so some 50 tons released, and I think that nobody wants to have their coast like that. So neither do I, or we. We started to think that, can we do something? So we can't forbid ship traffic, simply because there is Russia at the other side of the Baltic Sea. They need fairways to go there. And then we started to think in mathematical terms. If you talk about risk associated with ship traffic, then you have to go back to the fundamentals, understand what is risk. Risk is not uncertainty. Risk has clear mathematical definition. Risk is a product of probability of an accident, which is a non-dimensional measure. It's a ratio of two things. And the other part in the formula is a cost, which has dimension of money, euro, dollar, yen. So the risk has a dimension, and its dimension is money. If you think in those terms, and the risk becomes very clear and you can handle it, that's the only equation. Now you know all the dimension of it even. That's the only equation what you really need to know. So what we cannot do much as scientists here in marine science, we cannot reduce much the probability of accident, but we can maybe do something about the cost of accident. You know that if you break your leg in city, then it's bad. If you break your leg in desert, then it's fatal. So it depends where you break your leg. The same is true for ship accident. The costs, in some sense, they depend where it takes place. So if we go to the reducing of the cost of consequences of an accident, then the idea behind all this was that maybe we can send the ships over some different route so that if something happens, not necessarily, but if something happens, it happens in some sense in the most safe place. So it's a very simple thing to ask, but of course not easy to do. So what people typically do in marine sciences and oil pollution and pollution control, they try to find out where an oil spill will go after it has happened. Remember, after it has happened. So it's called the sort of direct problem in mathematical sense, and it is not easy to solve. If you put water particles here or oil particles, whatever, it may travel all over the Baltic Sea within a few weeks. If you put the water oil particles here on the surface, they may seemingly go wherever. If you make calculations by putting oil particles somewhere there, then within just one autumn day, the oil may cross the entire Baltic Sea. This is may, but not necessarily. It's just technical possibility of having oil at that distance, but it doesn't mean that oil really will go there. Now the question is where oil really goes. We started to look from a simple example, putting oil parcels along this medium line. They do go sometimes to the north, but very infrequently. They mostly come to us, and this is what we really don't like. With all my respect, my Finnish colleagues, you are somehow safe against oil pollution. So, and then a stupid question could be asked, maybe we should replace this, which is a model of ship lane, somewhere here. So, is it a logical question? So if from here it comes to the coast, so from here it maybe doesn't come to the coast, and it doesn't. It is transported out of the Gulf of Finland. So both sides will win. This was a simple question.
What about Sweden? It's not our problem, right?
Any Swedish journalists? I'll talk about this very soon. But that's a basic idea, where we should put the ships so that the pollution will not come to the coast. If oil pollution happens offshore, it is bad. But if it comes to the coast, then it kills the entire chain of life reproduction. So this is fatal, like breaking leg in desert. So what we asked, from where the pollution does not come to vulnerable spots. And this is the area where you should put possible oil spill, okay, to keep it there. Mathematically, we had to solve so-called inverse problem, which is in many cases theoretically not solvable. You can't propagate heat back to its source. It's fundamentally impossible. It's basically inverse problem. But it turned out that it was somehow possible to address this problem for current-induced oil transport. So we had to somehow quantify the offshore areas. What does it mean? We have temperature, we have salinity, and we put, for example, our fish farms into some favorable place in terms of salinity and temperature. So now we are going to calculate some other quantity which somehow characterizes the Baltic Sea or whatever world ocean in terms of safety. It's just another measure, but it doesn't matter for mathematicians, it's a number. So mathematicians forget everything which is behind numbers, they work with numbers. We need a number. And what we can do with a number, this is a density of whales near Boston Harbor. They're just numbers. So what was done a few years ago, the first case in the world, a ship lane entering Boston Harbors was shifted so that it became slightly longer by 15 minutes. For transatlantic crossing 2 weeks, it's nothing. But probability of hitting a whale was reduced by a factor of 2. So this is what I mean under quantification. Whatever terms characterize sea surface in terms of environmental costs, we can use that for manipulating our ship motion. Okay, that's the entire principle. Now it's what mathematicians did. They calculated this distribution in terms of cost of possible oil spill, what an oil spill would do if it would happen at some location. That simple is the mathematics. It wasn't so simple. We had to run ocean models for 40 years. We had to throw into ocean billions of parcels playing the role of oil, looking where they are going, and somehow bringing together their starting point and end point, and then looking from where it doesn't go to points where we don't want to see it. So the result was a new map of Gulf of Finland, Baltic Sea. This map shows you the probability, if you put oil parcel somewhere here, how long it will take for this parcel to reach the coast. This is just like salinity or temperature or depth. It's a measure which quantifies environmental risk, the time it will take for oil to reach the coast. This is extremely important. Typically, this time for the Gulf of Finland is 4 days. Remember this number, 4 days. Within 4 days, something happens to oil. Its weather's out, so some fractions are gone, some other fractions are going to deeper areas. So if you give oil some time, it is gone by itself. And you can also remove more oil by human activities. So time is a hard currency here. The most valuable thing, not the probability, but the time. And if you put the possible fairway like that, you will save the environment somehow. So you can, of course, make many solutions. The diplomatically correct solution is to share costs equally between Estonia and Finland. That would give you one line, which is definitely not optimum for the environment. This I can prove rigorously. And you can rely on probability of hitting the coast. It's very hard to sell it. But if you sell time, time is money. So again, back to the dimension of risk, which is also money. So time is equivalent to risk. You save one, you lose other. So saving time to environment actually is the basic result of the outcome. So those curves, which are in some sense optimum fairways, this shows how the cost should be, how it's possible to equidistribute the costs between Estonia and Finland. So mostly the fairway should come closer to Finnish coast, as was clear from the very first slides, and in some places it should come really close. But what is more important, you see that there is no implicit reason for those fairways to be shifted, to be asymmetric. Another thing is that there's actually a problem of maritime special planning. How you handle the sea area, which sea areas you allocate for which purposes. Just to illustrate slightly more in diagrams, what you have to look at some places, the optimum location of fairway, according to all criteria, sits at the same place, exactly at the same place. In some places, shift by 20 kilometers means nothing. So this is enormous, it's a really important thing to understand that seemingly very similar sea areas, by current structure, by temperature, by salinity, by geometry, they behave completely differently in terms of risk to the environment. And we have to know that. Otherwise we handle just improperly. Like people are all different. So we have worked out several exercises. Probably don't see much, but you see how different are the lines here. But the optimum line, which is this, for example, is only 70 kilometers longer than a standard line, which is not so bad. You can think differently. You can think putting weight on the environment and on economic costs. And depending on which weight you put, you may have completely different fairways. But look again, the optimum fairways seem to all to be slightly to the west. And this does have physical background. Every garbage which you put in the Baltic Sea will come to the eastern Baltic Sea coast, statistically. Sorry about that, that's circulation structure. Even those bizarre fairways, optimized by very strict conditions for being environmentally safe, are just 7% longer than standard fairways. So making a small detour, you really lose nothing. But you may gain 1/3 in terms of probability, and you may add up to 4 days to the existing 4 days of typical time of reaching the coast. So this is the real win. And this has dimension of money, as I demonstrated. We can draw nice pictures for different resolutions, but this is all what mathematicians love. You change resolution, you change some cost function, you get nice picture, and you are proud of that. What was more important in terms of maritime special planning, this sort of safety corridor for different areas and for different cost functions. There's some areas you can't go left or right. Whenever you go a little bit left or right, you increase potential damage to the environment immediately. But in some areas, you do have freedom. It's also important to know and to understand what is behind that. A major surprise for us mathematicians was that if we included also the wind here into the system, which does have clear effect, then for summer and winter, ships should go very close to Finnish coast to keep the entire sea safe. And spring and autumn, they should come close to our coast. So what is common for winter, which is windy, and summer, which is calm? This sort of miracle. In terms of navigation, they are the same. So this is now our task to prove to the decision makers that actually the fairway should change according to seasons. It is hard to explain that to politicians, so why Finland should accept heavy tankers according to coastline, but it's balanced by a request that Estonia should accept the same, but during another season. Okay, I think that this is perhaps less interesting, just a picture of how dense our shipping network within just 2 weeks in November 2009. And the marine protected areas, which are our first concern and politically correct concern, we should avoid pollution going there for first. but some of those areas, like this, is safe per se. So just they are safe. Currents do not bring pollution there wherever you put the pollution. And some areas got pollution almost all the time. So this pattern, we don't understand why it's like that exactly. It's quite fresh result. And the other thing is, if you take just one relatively safe place in terms of coastal pollution, you still see that almost the entire fairway may be a source of pollution which reaches this particular marine protected area. So shifting fairway just so, it's not only sensitive politically, but there is not yet a clear solution which part we should shift and in which times of year. I think do not. That's for scientists. The essence is that we have understood that the risk, even in terms of environment, has dimension of money. And if we save environment, we save our money. We have written perhaps, and the book will appear from print in 2 weeks, 442 pages something. That's a short explanation of mathematics behind. I have even the cover somewhere. But I think we all would like to have covered coasts like that.
Thank you.